Bismillahirrahmanirrahim. In this unit, we will discuss the formation of energy bandgap in material. The formation of energy bandgap in semiconducting material is a fundamental concept in electronics that explains the many electrical and optical properties of semiconductor. Firstly, we discuss the isolated atom of any semiconductor. In isolated atoms, electrons occupy discrete energy level or orbital, which are defined by quantum mechanics. Each orbital corresponds to a specific energy state that an electron can inhabit. These energy levels are quantized, meaning that electron can only exist at certain predetermined energy level and cannot have value in between them. For example, in a hydrogen atom, the electron can only occupy a specific energy state 1s, 2s, 2p, etc. And the energy of these levels is determined by the principle of quantum number, generally referred as n. The arrangement of electrons in these orbitals define the chemical properties as well as electrical properties of atom. The innermost orbitals are filled first, and as an atomic number increases, electron fill the higher energy level. This discrete nature of energy level is fundamental to understand the atomic behavior and chemical bonding, which in turn play a vital role for energy band gap. When silicon atoms come together to form a solid, the atomic orbital of adjacent atoms begin to overlap due to the close proximity of the atom. And the overlapping occurs as the atom approach very close to each other and causing their energy level to be interact. In a solid, the individual atomic orbitals no longer maintain their discrete energy level and they do in isolated atoms. Instead, the overlapping atomic orbitals create new energy states that are not limited to the original atomic level. This phenomenon is result of the quantum mechanical principle that neighboring atoms influence each other's electronic configuration. For silicon, which has four valence electrons, each atom forms four covalent bonds with four neighboring atoms in a tetrahedral arrangement, leading to the formation of crystal lattice structure. As these orbitals overlap, they modify the energy level available to the electron, which is essential for the formation of energy band. The overlapping of atomic orbitals leads to the formation of molecular orbitals, which create continuous energy bands in a solid. As more atoms are added to the solid, the number of overlapping orbitals increases, resulting in an extensive range of energy. These energy levels consolidated into two primary bands. Valence band. This band consists of energy levels filled with electrons involved in bonding. In a pure silicon crystal, these valence band is fully occupied with a absolute at absolute zero temperature. Similarly, conduction band. Conduction band is relatively a higher energy band and they contain levels that can accommodate free electrons. Electrons in this band can move freely, allowing for electrical conductivity and many other electronic properties. The energy band gap can be defined as the energy difference between the valence band and the conduction band, and generally referred as a EG, energy band gap. This band gap is critical in determining the electrical and optical properties of semiconductor material as discussed above. In silicon, the band gap is approximately 1.1 electron volt, which allow it to behave as a semiconductor. The ability of the electron to transition from valence band to the conduction band, often facilitated by thermal energy, optical energy, or some doping enable intrinsic and extrinsic semiconducting beam. This property is fundamental in the operation of various electronic devices, including diode and transistor. A band gap is the energy difference between the valence band of electron and conduction band, as we have already discussed. And essentially, the energy band gap represents the minimum amount of energy that is required to excite an electron up to a state in the conduction band where it can participate in conduction. The energy band gap is a critical property that distinguishes conductors, semiconductors, and insulators. Here's a detailed overview of how the energy band gap affects each type of material. Firstly, we discuss about conductor, and as you know that conductor has energy band gap of 0 volt. In conductors such as metal, for example, copper, aluminium, the valence band and conduction band are completely overlapped. This means that electron can move freely, facilitating electrical conduction without the need of any further additional energy. The absence of energy band gaps allow for an abundance of free electrons, which contributes to high degree of electrical conductivity. Conductors can easily carry electric current, making them ideal for wiring, ohmic contact for electronic devices itself, and even ULSI and VLSI IC. Another classification of material on the basis of energy band gap is semiconductor. Semiconductor has a small band gap, typically in the range of zero point 0.1 electron volt to 3 electron volt. It is not a fixed value. It varies, depends on the nature of the material itself. Some organic and polymer have a higher energy band gap, even greater than 3 electron volt. Semiconductors, for example, silicon, germanium, possess a moderate band gap, which allows them to conduct electricity under certain conditions. At absolute zero, semiconductors behave like insulin. However, as temperature increases or when doped with impurities, electron can gain enough energy to jump from the valence band to the conduction band, creating free charge carriers. These carriers may be electrons as well as holes. The band gap size determines how easily electron can be excited. For instance, silicon has 1.12 electron volt. It's commonly used in electronics due to their balance between conductivity and thermal stability. On the other hand, gallium arsenide, which is another very important semiconductor material, has energy band gap 1.42 electron volt. And this energy band gap is favored in many electronics application due to its direct band gap. Insulator, third classification on the basis of energy band gap. Generally, insulator have very large band gap. For example, greater than 3 or 4 electron volt. Insulators such as rubber, glass, diamond, and many other materials, ceramic materials, have a significant band gap, which prevent electrons from moving freely between the valence band and conduction band. The large energy gap means that a substantial amount of energy is required to excite electrons into the conduction band. As a result, insulator exhibit very low conductivity, low electrical conductivity. And insulators are essential for prevent unwanted electrical current to flow in electronic devices as well as ICs and particularly MOSFET when gate in between gate and channel we provide oxide layer to avoid the unwanted flow of electron from gate to the channels. And these semiconductor material demonstrate a diverse application of bandgap energy, which directly influence their electrical and optical properties. Direct bandgap semiconductors such as gallium arsenide and zinc oxide are particularly effective for optoelectronics application, while indirect bandgap semiconductors like silicon and germanium are crucial for traditional electronic devices. Understanding these properties helps in selecting the appropriate semiconductor for specific application and driving advancement in technology across various fields. It is important to understand the importance of understanding the units used for energy as electron volt. In figure, the unit of measured are written as electron volt EV. The unit is appropriate because W, which is the energy, can be defined as a QV, and it is deriving from very simple equation. The voltage is equal to work done per unit charge. And substituting the charge of 1 volt and potential difference of, charge of 1 coulomb and potential difference of 1 volt result in an energy level referred to as a 1 electron volt, where Q is the charge of electron volts and its unit is 1.6 into 10 power minus 19. When it multiplied by 1, so it is equal to the 1.6 into 10 power minus 19 joule. And 1 electron volt is equal to 1.6 into 10 power minus 19 joule. In generally solid state electronics, we refer the unit of energy in terms of electron.